Hello everybody. So this is meant to be a review of our activity with the pendulum and the spring. And so I'll just make a few comments here and some discussion. The solutions to the entire activity are posted on Blackboard. Please look at those for more detailed solutions, but I'll have a little narrative here to just talk about the things that matter in this lab and the things that we noticed from our simulation activities. So as you tried, you had a pendulum, and so part of the reason for us to be jumping into this kind of activity was to be gripped by the necessity of trying to figure out a way to create a language for ourselves to communicate what's happening. And so here's a picture that sort of describes what it is that we were looking at. So you were asked to try and figure out something about the amplitude of the oscillation. Well, you didn't really know at first, well, what should I pick for my amplitude? Well, as you looked around at the different variables, it became apparent that however much you pulled this pendulum back, there was an angle that actually, I guess it was just a little bit above where the pendulum was. You could see a number changing, and that number was the angle in degrees that you pulled this pendulum back. And so we took a look at that and said, well, okay, so maybe that's the amplitude then, so the degrees to which you pull it back. Now, you might think, well, I don't know, was the amplitude like from the center position to the edge, or is it from edge to edge? And so this is actually a little bit of a matter of convention, but the convention is, I think, tried and true, which is that if the amplitude is representing the amount at which an object is pulled away from its equilibrium position. So its equilibrium is where it would finally rest if you just finally let it go, let it do all of its oscillations, and eventually it would settle here at the bottom. So if you pulled it away by 15 degrees, which is what it looks like here, the amplitude would be 15 degrees. The mass is just simply the mass of the bob, and the length, even though it's not shown exactly here with this arrow, is the length to the center of this bob to the pivot point. And that's the length, and it's technically, I guess, even though the slide here says the length of the string, it's actually the length that goes all the way to the center of mass of your object. So that way, if you had some kind of big rock, that arrow or that length would point to the center of wherever that rock is. And technically, it's called the center of mass, but there's some limit about how detailed we'll get here. So, all right. So, what were some of the things that you noticed that you found out from doing this experiment? Well, we were trying to figure out, as I changed each of these things independently, how does it actually affect the period and thus the frequency of the pendulum? So you had made some predictions. You tried to figure out, well, what things do I think would change it, and which things do I think might not make any difference? And some of you were actually very surprised in this case. Many of you thought that because of the earlier activity we had done with the ruler, remember putting a ruler at the side of the table and watching it float up and down, that the more ruler there was, the more mass, and so it took a longer time for it to go up and down. You thought, well, maybe that's the same thing for the pendulum, but it turns out that was not the case. So, what things mattered? Well, if we changed the mass, we found that the period does not depend on the mass. Well, you can think of it because the more mass there is, it's true that there's more mass to be moving, but there's also then more tension in the string, and that's actually pulling it back. And so those things change together, and it turns out that the period does not depend on the mass. The amplitude, at least to first order, does not depend on this A. So the A in this case would be theta, would be how far away you bring it from the equilibrium. So you tried 10, 20, 30 degrees. You found that you really didn't see much trend. It didn't appear. Now, it does turn out that if you were to keep going, you would actually find out that there is a slight deviation once you get beyond, say, about 20 degrees or so. So, but changing the amplitude in this sort of small angle range actually doesn't make any difference. Finally, the period does depend on the length. If you increase the length of the string, the period increases. So what does it tell us about the frequency? Well, we remember that frequency is 1 over t. So that tells us that as we increase L, the frequency decreases. If I wanted to have a high frequency, in other words, tick-tock, 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 I should make the length of the string really short. So I want you to develop some intuition about that as you go. Connect your intuition to the equations. Next, we had a mass on a spring. This was also a simulation. We had something like this set up here. We had some mass. We could vary the mass. We could change something about the spring constant. And we watched this thing bob up and down. So the questions that we asked ourselves were, what can you change about a spring and mass system to make it cycle faster or slower? The faster would mean a higher frequency or a shorter period, and slower would mean a longer period or a lower frequency. What factors do you think determine its period? Well, so the things that we have to play with here are the mass, the amplitude that we pull it to, and then something about the spring constant. So you can look at all those things here. Which of the following things really affect the period of the mass in a spring? Is it its mass? Is it the spring constant? In other words, how stiff the spring is, how like strong the spring is, something like that, property of the spring. Or does it have to do with maybe how far we pull this thing? If we pull it further, would it maybe oscillate faster? Maybe. So those are the things that we investigated. And we found that the period does depend on them. If the mass increases, the period also increases. And so the way we can think about that is that spring is not going, unlike the pendulum case, that spring is not going to change the amount of force or the amount of pull that it can have on the mass if you change that mass. Those two things are independent of each other. And so if I'm increasing this mass, then it's going to take more time to move, so it has more inertia. The spring constant K, the period does depend on the K. As K increases, that means it becomes a stiffer spring, and then the period decreases, or in other words, the frequency increases. So imagine like a suspension spring for a car. You can look that up on Google. You can see that those are really hefty springs. If you were to give it a little pluck and kind of like pull on it, it would go boing. It would be like a very fast oscillation because the spring constant is very high. And then finally, you tried different amplitudes and you found out that, you know what, if I pulled it by 5 centimeters, 10 centimeters, 20 centimeters, it doesn't matter. It's still going to, if I don't change anything else, it's still going to go up and down the same number of times per second. Okay. So let's think about how to graph these kinds of things. So if I were to swing a pendulum back and forth in cycles, what does a graph of the position versus time look? Well, I might plot like angle as a function of time, or I might look at like the shadow on the ground. Like if I were to have I don't know, a big light here on the top, and I would shine it down, and I would watch how the shadow moves back and forth across here. So let's say from +5 to -5. So it might look something like this. We might see that the position, maybe the projection of this thing, let's say here from -10 to +10, is going to be going back and forth as time marches forward. So imagine like that you have some receipt paper, and the receipt paper is just moving out steadily, and you're standing there with a pen, and you're just dragging the pen back and forth perpendicular, and you would actually see this kind of motion start to, this kind of pattern would arise on the paper. So this graph shows you repeated cycles. In other words, if I started here and I waited for, it looks like 7 seconds, then after 7 seconds, this motion would repeat itself. And here we go again, another 7 seconds, we're up to 14. Another 7 seconds, up to 21, etc. And so you can see that a one cycle means the time that it takes for the motion to completely repeat itself. Not to go from, say, -10 to 10, but to go from -10 to 10 and back to -10. That is one cycle. So that's a complete cycle, and we say that the amount of time that it takes for an oscillator to complete one cycle is called the period. So what is exactly happening here? Is it stopped here? Is it moving? What's going on? I'm going to pause here and let you think about that for just a moment. Talk it over. If you're watching this with a friend right now, take a look and say, what is happening here? What is happening here? And why? Okay, we're back. So the idea here is that the position is 0 here. Well, that would be the equivalent of, if you can see this sort of shaded a pattern to remind us about the pendulum here, this would be that the pendulum is moving through the center position here. So it's actually moving the fastest right there, and it's actually at its kind of equilibrium position, even though it's not in equilibrium at the moment. It's moving quickly. Now here represents a turnaround point. This is at -10. This is a moment where it's stopped. And so those are some things that we can gather from the motion looking at this graph. So this was part of our worksheet here. Graph these data points on your assignment sheet. And we wanted to see if there's a pattern. So we had to look for the number 2 on the sheet, and then like Battleship coordinates, if you've ever played the game Battleship. If you haven't, maybe just look it up on Google here. It's a kind of a children's game, but it's also fun for us too. And you just look for the coordinates 2 on the x-axis and 16 on the y-axis, and so on. And you'll see if there's a pattern. When you plot them, you'll get something like this. And you might think, nah, I don't think I did it right. I think there's no pattern, right? So you look at all these things, and you see all these different points around, and you think, well, I don't know. I don't know if there's a pattern or not. You could draw a lot of different kinds of lines through these things, but there is one line, not line, but one curve, which goes through all those points, and it actually makes sense. It's a sinusoidal line. So look at that. It's not easy to see that at first, but now looking back on it, you can think, oh yeah, I guess that is, right? So I guess those are points that make up a sinusoidal curve, right? And so there is a pattern. And if we weren't sure if there was a pattern, one strategy that we might have is to just take more data points. We want to learn more by just simply trying out some more measurements, and then we'll get really clear on it. We'll start to fill in a dot here, a dot here, a dot here. And you notice that it actually goes above and below the number 12, right? So that's interesting. So we don't have to necessarily have the equilibrium position be actually 0. And one of the things we found in our activity was that we didn't need to have it be at 0. That it can be at 12. And then you can see here is that one of the things I noticed is that it goes above 12 by 4, and it goes below 12 by 4. So this means that the amplitude, this is the maximum displacement from the average value. So the average value, if you took all those points and you average them, you'd get this number 12. And if you took the maximum, you'd get 16. And all you got to do is subtract the 2, and you will get the amplitude of the motion, which is 4 meters. Now you might also notice that it's 4 meters below as well. And but that's the way that we figure out what the amplitude is for any motion. Similarly, we want to figure out the period of the motion. Well, if you look here and you say just take any point and you go around one complete cycle and you get to here, you'll notice that it takes 9 seconds to repeat the motion. Or if I go here from this peak here, at looks like a little after 11 seconds, and I go over here to a little after 20 seconds, you can actually see that that's 9 seconds in between. So you really can just pick any point and then move to the place where it looks like the same, and you'll find that this is repeated. And so sometimes it can be a little tricky to figure it out exactly. And so, that's where sometimes using a ruler, if you have a piece of paper, just trying to figure things out, that's a good way to figure those things, to read those off of a graph. So some of the skills that you're learning here from this activity, hopefully now that you're looking back on it, is that you see that you can measure the period and the amplitude just by reading it off the graph. So finally, we should talk about the frequency. Well, how is the frequency related to the period? Well, frequency is just 1 over the period. So apparently, if I took this period, the 9 seconds that it takes to repeat itself, and I asked myself the question the other way around, which would be to say, how many cycles are completed in 1 second? So how many cycles per second are there? And you can see here that, well, I'm not doing a whole lot of cycles in 1 second. In fact, I'm doing a fraction of a cycle in a second. So, in other words, if I took here from 6 to 7, that's 1 second, then I would see that the amount of cycles that I go through is less than 1. So, in fact, by taking 1 over 9, I can see that the frequency is 0.11 hertz, and that is the amount of that's the amount of a cycle that I went through in 1 second, and so that's what we would write down for our frequency. So just to review, the period of an oscillator is 1 over its frequency, and the frequency of an oscillator is 1 over its period. So Hopefully that, along with the solutions provided, will help you to feel like you're beginning to master the concepts of activity on period and frequency.